Okay, so in this torque review question, it's as much about the moment of inertia as it is about torque. But let's jump in here. We've got an L-shaped object shown at right, or shown below essentially. It can be rotated in one of the following three ways. Case 1 about the x-axis, case 2 about the y-axis, or case 3 about the z-axis, which passes through the origin perpendicular to the plane. And the same torque is applied in each of the three cases, rank them in order of resulting acceleration. And that should be angular acceleration. So I'll just use the space down here to consider. So alpha is equal to torque net divided by the moment of inertia. So we're applying this. We assume we're applying the same net torque to each situation. The alphas will be inversely proportional to the moments of inertia. So the key thing here that you need to know is that the moment of inertia of a particle is simply just r squared, where r represents the distance from the mass to the axis of rotation. So if we consider the case 1, we're rotating about the x-axis. So sometimes this is visually hard to imagine, but about the x-axis, if we were to rotate about the x-axis, so we'd be rotating along the horizontal, the only thing that would really be rotating is this 9 kilogram mass. The 1.2 kg and the 2.5 kg are already on the x-axis, so their R value is 0. So these two masses don't have any moment of inertia about the x-axis, because again they're on the x-axis, so their R value is 0. So in case 1, the moment of inertia in case 1 is just going to be the moment of inertia of the 9. So that would be 9 kgs times 1 meter all to be squared, which is just 9 kg meters squared. So for the alpha in case 1 would just be the torque net, which is the same for h1 divided by 9 kgs meters squared. In case 2, I'm trying to get this all on the same page here. So I2, the moment of inertia in case 2 is rotating about the y-axis. So now in this particular case you've got the 9 kg and the 1.2 kg. So in this case it will be rotating up and around, or spinning in this sort of direction. But these two again are located on the y-axis, so they don't have any moment of inertia. So it's just the 2.5 out here. So in this particular case this would be equal to 2.5 kgs times 2 meters all to be squared, which will become 4 meters squared, so 4 times 2.5 is 10 kgs. So this is very similar to alpha 1, but slightly smaller. Since the I2 is bigger, the alpha 2 will be smaller than alpha 1. So this will be the torque net, which is the same for all, divided by 10 kgs per meter squared. And I'll do I3 here below the box here. So I3 is a little more challenging, because in this case we're rotating about an axis that is perpendicular to the page. So this time the 2.5 and the 1 are spinning around in a plane that's parallel, or a plane that's in the same plane as the page. So you got the 9 and the 2.5 spinning around. So again, I've got the 9 kgs times its 1 meter squared, 1 meter all to be squared, which will be equal to 1 meter squared. Oops, plus the 2.5 kgs times the 2 meters all to be squared. So this is basically the sum of these two, which is 19. So this will definitely be the smallest. So alpha 3 would be the torque net divided by 19 kgs meters squared. So in this example, alpha 1 is the biggest, then followed closely by 2, and then 3 is quite a bit smaller. So yeah, it's just 1, 2, 3. So 1 is greater than 2 is greater than 3. So choice E.